Okay, so welcome everybody to our penultimate talk of the topology seminar this semester. Today we are happy to have Oishee Banerjee from the IES who's going to tell us about cohomology and arithmetic of some mapping class spaces.
Thank you for the invite. I understand that there can be some problem in transmission on Zoom. So if I write something or say something that's not legible, please do let me know. Okay, so let's go to the basics, the what, why, and the how. So what about mapping spaces do you want to talk about? So this will involve the kind of mapping spaces that I want to talk about, as well as the specific questions that are going to be the focus of this talk. And as far as cohomology and arithmetic is concerned, being a topology seminar, I will focus more on cohomology. And the questions are the why asks. Why should we care about the cohomology and arithmetic of these spaces at all? And how do we go about it? So the why will involve some history and motivation behind studying these spaces and the spaces that I'll talk about soon. And the how will probably be the last 5 minutes of the talk about some methods. So the mapping spaces that we specifically want to focus on is generally we can fix some X and Y, some topological spaces, manifolds, algebraic varieties, whatever. And in that category, we can consider the maps, the moduli space of maps in certain sense, when it makes sense, need not be even non-empty. The ones we will consider are the algebraic maps. Typically, they will be denoted by more dxy, where more stands for morphisms. And D is some suitable notion of degree, or some notion of some degree, which will become apparent as we go on. One can also consider holomorphic maps, because when the base field, when the K is a C, and X and Y are like, say, smooth and maybe projective, it's sort of same to consider the space of holomorphic maps. Much less appearance the space will make, but it's equally important, is the space of continuous maps, which we will typically denote by map. And as you can see, all of this have some notion of degree, which will become apparent soon. And note that there are these natural inclusions. The holomorphic maps sit inside the space of continuous maps, and so does the algebraic maps, which I denote by more. And even though we won't make much comparison about this guy and this guy, all three of these will come up when I talk about the motivation behind considering cohomology and arithmetic of some of these spaces. Okay, so this is pretty much about what. Now the thing is about why. So a bit of history. One of the so the history involves a part of the history is going to be about the cohomology part, or more generally the topology part, and part of the history is going to be about the arithmetic part, why number theorists care about certain of these mapping spaces. So let's start with the topology side of the story. So suppose X and Y are just, I'm going to write P1. So this is, you can think of it over complex numbers, in which case it's CP2, the two sphere, And more generally, one can also consider X to be a Riemann surface, or equivalently a smooth projective curve. And in that situation, so I want to consider the space of, I'm going to write the space of degree D algebraic maps, let's say from P1 to P1. And this will be the same as the space of holomorphic maps as well. So let's just, for the sake of writing down some definitions, see what this space is. This is like a pair of polynomials, f and g, where these are of degree D, homogeneous in two variables. Let me write it like this, such that the resultant is non-zero, such that f and g have no common zeros. Right. So this is the key part, sort of like no common zeros. Otherwise, you won't have a algebraic or holomorphic map. So what Siegel did back in 79, I think, is that he showed the space of degree D maps from holomorphic maps from CP1. Let me be precise. So this is naturally sitting inside the space of, I should write, these are based maps. So say infinity goes to a fixed point somewhere, based maps. To the space of continuous maps, and this is a homotopy equivalence up to a certain degree. I think that's d times 2n minus 1, if I'm not mistaken. And this started a flurry of activities where people started asking, okay, instead of projective space, what if we take something else, like say a Grassmannian or a flag variety, or something called a smooth projective toric variety. So how far can we, so when you have a result, you want to push it somehow. And there was some progress back then. In some cases where there is some natural group action giving you lots and lots of maps. So I want to mention that over C, so now the ground field is going to be C for a while. Francis Kirwan shows, I think it was in 84. I'm not 100% sure, so I'm not going to write the year. So in the case of Y being Grassmannian, so she showed something like the space of holomorphic maps from CP1 to a Grassmannian is homotopy equivalent to the space of continuous maps up to a certain degree. And Martin Guest worked out the case of when Y is a smooth projective toric variety. I won't get into the definition of what a toric variety is, but some examples are like projective spaces, products of projective spaces, weighted projective spaces, projectivization of a vector bundle over a projective space, for example, and so on. Okay. So I want to highlight what goes behind something, proving something like this. All of them had one key ingredient, which is called the scanning map. So Siegel used scanning maps for his results, which was generalized by Kirwan and Guest later on. And I want to highlight one thing. It's something that is very specific towards works specifically over C when the ground field is C, because it involves sort of taking tiny neighborhoods in the analytic topology. And the reason I want to highlight this fact is that if one might wonder that, okay, instead of like taking the complex numbers, what if we want to do the whole thing such that it works for like any algebraically closed field? Well, the space of continuous maps would not work in the traditional fashion, but nevertheless, if someone is interested in, say, stable homology questions of this space, one can still want to compute it so that it works for like whatever the ground field is, and none of this scanning map technology will work. Okay, so as beautiful as these methods are, if you wanted a topology over more general fields, you're kind of stuck. Okay, I want to now talk about the arithmetic part of the history and motivation. And before that, I want to mention that on this note, there came up a Cohen-Jones-Siegel conjecture, which says that when Y is what is called a Fano variety, I will say in a moment, I won't give the general definition, I'll give some examples. So when Y is a Fano variety, the conjecture says that the space of morphisms, the space of algebraic maps from P1 to Y, sitting inside the space of continuous based, I keep forgetting that. Okay. Space of algebraic maps sitting inside the space of continuous maps is a homotopy equivalence. Up to some degree, maybe. That some degree depends on Y. So what is Fano? Think of, so the technical definition is that it has the anti-canonical bundle to be ample. That's the algebra or geometric definition. But think of, so it consists of like all flag varieties, toric varieties, their products, blow-ups of these guys. Nice generalizations of, this is a very loose statement, of course, of projective spaces. And one super hard situation where this conjecture is still not known is the case when Y is a hypersurface in like CPN, like cut out by some homogeneous polynomial. Y is a low degree. Yeah, so suppose, so in CPN, you have homogeneous coordinates given by x0 to xn, right? And you can write down some degree m homogeneous polynomial. So when m is low enough, that Y happens to be a Fano variety, and these sort of answers, comparison between the algebraic space of algebraic maps and continuous maps is wide open. So that's a big motivation on the topological side. On the arithmetic side, any questions or comments so far? Okay, so the arithmetic side, on the arithmetic side of the Y, there is this thing called geometric Monin's conjecture, and I won't state the conjecture in full generality, but I'll say sort of what motivates things. So there is the dichotomy of like number theorists have this dichotomy between number fields and function fields, where so the rational numbers on one hand can be replaced by sort of so this is a function field of function field of P1 over a finite field, and number fields which are like finite extensions of the rational numbers, their counterpart is like so if you have a not exactly a Riemann surface, but the algebraic counterpart of it, which is a smooth projective curve, and you take its function field, then what Monin's conjecture says is that so originally Monin had a conjecture about these k points of a variety. What we want, or what we want to talk about is FQC points of a variety Y, and this is the geometric Monin's conjecture, which says that there has to be like there can be up to some certain number of points. It gives bounds. The conjecture gives bounds on the number of points. But effectively, the reason I'm bringing it up is that if you replace instead of the finite field business, if you replace these by say the complex numbers, then what you have is an S2 or a Riemann surface, and these function field valued points in a variety Y translates to over C. This translates to the space of maps from just so this variety over C, right? So essentially, you can consider the space of maps. You can think of its complex points, in which case you get back kind of the things that Siegel and Kirwan and others studied, but also you can consider its finite field points, and they have actual number theoretic implications. So that's, of course, from various sides, motivation enough to consider a certain moduli space of maps. Any questions or comments or suggestions? Okay.
Sorry, I have a question. So can you repeat what is like the C without like the non-complex C? Like what is that?
The non-complex.
Like so FQC, what is like C in that bracket?
Could you repeat your question? I don't think.
In the function field case, you have like FQT and then below is FQC. Yeah, so what is the C inside the bracket?
Ah, my bad. That C, okay, there are too many C's. That's a problem. This C is a smooth projective curve over the finite field, and over complex numbers, this is equivalent to how considering a Riemann surface of genus whatever.
Cool.
Okay. I'll just write Riemann surface, even though that's over FQ technically not correct. Any other questions? Okay. So now what we do is on the topology side, the positive results are these homotopy equivalences up to a degree. On the arithmetic side, as far as these number field cases has been much considered by like people like Peter Sanak, Yuri Chinkel, and others. This is not our focus. Function fields are more what we are going to be concerned with, and more specifically, we want to consider curves over any fields whatsoever, and so that we can talk about like complex numbers or finite fields in equal footing. And so far the positive result in the world of function fields, as far as geometric models is concerned, that do not use these homotopy equivalents, is that of Browning and Savin from 2017, where they consider the case of Y being a hypersurface, low degree hypersurface, so cut out by a homogeneous polynomial like here. And what they do is, using analytic number theory methods, they actually compute, I wouldn't say compute, they gather information about the stable cohomology of this space and use it in a way to verify the geometric Martin's conjecture. Okay, so that's so far about history and motivation. So what we want now is sort of to fill up this space, which consists of, so it seems that the topological methods are very much methods which work over C. And if one wants to sort of have a method that plays well with both topology and arithmetic, in the sense of like satisfying algebra geometric data like hot structures, etc., there is no method filling that gap. So outside of topology, one has to go to the other end of using analytic number theory to answer some special cases. So the goal is now to sort of try to fill that gap as much as possible. So I will just write the question down to be precise. So what if Y is not smooth? The Y being the target space for receiving the maps from the Riemann surfaces. And that cannot happen if you stick to the world of manifolds, but that can happen if you want to, for example, ask about like more general toric varieties. Like even for a weighted projective space, one would get into trouble if one tries to do strictly analytic small ball sort of method. So example. Blow ups, etc. Also, another matter of concern is that what if your Y is not even a variety, but something like even the nicest possible stack, like say a weighted projective stack, which is, what if Y is not a variety or a manifold? For example, what if Y is something as simple as you take the complex projective space, you take out the origin, and you take the quotient by the non-zero complex numbers, where the action is something like lambda takes a point x0 to Cn plus 1. this will be, say, lambda to the t0 x0 comma lambda to the t n xn, where the GCD of t0 to tn is not 1. So in such a situation, the space that you get, every point has a non-trivial stabilizer. And it's not an orbifold even in the traditional sense. And one wants to have a method which plays well in the topological sense, like that you can actually compute just like singular cohomology. But at the same time, if you want to compute like L-adic cohomology, then also you can do that. So thanks to the language of sheaves and Grothendieck six-pointer formalism, this sort of thing can be done. So that has been done in various ways and much explored. But that is sort of the savior to the situation. Okay, so any questions or comments so far before I get into some sample results and computations? No? Okay. Okay, so I want to just spell it out. For computing, let's say homology may or may not be with compact support, whichever we get, of things like this with some coefficients. And so motivated by these questions, what we do is, in many cases, so no matter what the case is, one can cook up a spectral sequence using more general methods. Having a spectral sequence to compute cohomology need not mean that that will be actually computable in real life. And in nice cases where if you have, say, nasty toric variety with singularities, you can compute the stable cohomology, and you be it over complex numbers or be it over finite fields, and thereby have answers in terms of, in the topology world, have answers in terms of homological stability, and in the arithmetic world, you have confirmation of geometric Martin's conjecture. Okay, so I want to state a couple of sample theorems to this end. I will not state the most general, the theorems in the most general form, because that will take pages. Okay, so this is probably the precursor to how. So the first thing I want to state is a spatial case of it was written in 21. A more general case is in 23, but I will just state the special case. So suppose you have, suppose X is a module over a graded commutative monoid sim M, where M has, suppose, some grading. Let me write it like this, E. Having a module over a graded commutative monoid isn't enough for what I'm going to write next. There has to be some very minor additional condition that I will not get into. So with minor additional Channel condition. Okay, and let U denote X minus M cross X. Just the complement. Right. Then I will write down. So I'm going to write the actual result has been written down in the language of sheaves, but like sheaf cohomology, like with coefficients in constructible sheaves, and like singular cohomology, they are isomorphic. So, and the result holds in chain complexes in both senses. So I will write down both. Right. So this is maybe. But as I said, like most of the these theorems, since they are aimed towards applying in explicit cohomology computations and their number theoretic implications, we use the language of sheaves, and in that case, it looks as follows. This is the right one, right two.
Oishee?
Yes.
Okay, I think we lost you since like the beginning of the first condition, of the first statement.
This statement, right?
Yeah. So like your voice disappears starting then. So
yes. So I will explain. Once I write down, I will explain what I'm writing. Yes, that's. Thank you.
Thanks.
What I want to write is this. Right. Okay. So I have written you statements with a bunch of symbols, and now I have the responsibility to explain the symbols. So wait a second. J is the map. J is like, so U is the complement. So J is the map that's embedding U in X, the inclusion map, and omega X. These are dualizing sheaves. Okay, so statement one. What happens is this X will be this X will typically be, in our cases, in the examples that we'll look at, you can think of it as the space of those maps. Let's say maps from P1 to P1, but a certain closure of that, not just that. So that F would be, in our case, almost always a P1 or a Riemann surface. And one can, the X will have the compactification of these mapping spaces that I want to talk about. They will naturally have a module over this graded commutative monoid structure. And in turn, having this minor additional condition, whatever that enables you, it enables you to say that this guy, the chain complex over X is actually in turn a module over this graded commutative monoid, and the derived indecomposables are precisely the naive indecomposable in a sense. So X being a module over sim M, X has an action of sim M, right? And one can think of, like, one can try to understand what the complement is, like literally it's a theoretic complement. And that's a topological space. And this is a relation which one can dub as, like, this is what is called derived indecomposables. And I'm not sure where it first makes an appearance, but the definition that I'm using is it makes a prominent appearance in Galatius, Cooper's, and Randall Williams' work. So this is a derived tensor product, and the derived tensor product gives you indecomposables in a sense, and here they are indecomposables in chain complexes. And it need not be the case that these indecomposables in chain complex are actually supported over U, but sort of the takeaway is that they are indeed. And this part, this is just the shift theoretic analog of that, which we need not get into. I wrote down because in case if time permits, I will make a computation, and in that case, they might appear well. Otherwise, this need not be the focus right now. Okay. So I've thrown a bunch of words and symbols, but let's not forget the motivation for even writing anything down. Writing this theorem down. So I want to I want to write down an example where this is actually used. So let's take the simplest example, which is just maps from P1 to P1, be it holomorphic or algebraic, something that Siegel considered. Okay, so I guess this is sort of the how part. So example. So let's consider the space, the moduli space of degree D maps from P1 to P1, which was a pair of degree D homogeneous polynomials having no common zeros. Homogeneous, yeah. Okay, and now let's take X to be the disjoint union of something that I'm going to call as more twiddle. And I'm going to define it as that you forget the no common zeros condition. So that's pairs of all polynomials of degree D homogeneous in two variables up to scalars. So in particular, for each D, this is isomorphic to like projectivization of C2D plus CD plus 1 cross CD plus 1. So this is for each D, right? Is everyone with me? Okay. And there are natural maps. So X is a sim P1 module where sim P1 is the disjoint union of n symmetric products of P1 over all n, right? Okay, and the module structure is given by, so let me just write this, P1 cross so the module structure is given by these maps where suppose you have a point A, B on P1, right? And you have a pair of degree D homogeneous polynomials, which may or may not have common zero, you don't care anymore. And you map them to let me write ay minus bx times f and ay minus bx times g. And you can define this map for any d, and you can define this map for any number of p1. So you can define this map for like sim n p1 for any n whatsoever, right? You just multiply these factors. So whenever you have a point of p1, you can just put it in as a linear factor so that whatever the image is, it vanishes at least one point in p1. So the image of this map precisely lands in the part where a pair of polynomials have at least one common zero. So it lands right in the complement of the space of morphisms. So this more, so this guy is sorry. So, so when I write minus something, it's the image of this guy under this map. So this is a situation where the format sort of resembles whatever the statement of the condition of the theorem was, right? And it's sort of natural now how, or this sort of motivates why you want to call something decomposable and indecomposable. So your decomposability is sort of naturally like being able to extract common zeros. That shows the decomposability, and the indecomposability in a naive sense is where a pair of polynomials do not have any common zeros. Any questions so far? Okay. So the theorem statement said now that so we're going to apply the theorem to compute the cohomology of, so okay, apply theorem to compute cohomology of and even though I'm writing things down in terms of like one need not even assume complex numbers, even though I've written things down like that, like any algebraically closed field works. Okay, so what we're going to do is, so the theorem statement says that you have this derived tensor product at the level of chain complexes, right? So what I'm going to write it as is the derived tensor product can be, so you can take the actual chain complex resolution of that, and if you take the so cx, there is something like this, right, in the statement. So this can be so you can use say Kazoo resolution, and effectively what you'll get is like terms like the associate the associated graded part is given by something like C, the chain complexes tensored with over sim. Sorry, this looks pretty ugly. So this is the associated graded of this guy, right? And now, according to the theorem, this is the same as the chain complexes you have over U, so that when you take cohomology, you get a spectral sequence. Taking cohomology gives spectral sequence, which is like, so it's an E1 page spectral sequence where you have the qth cohomology compactly supported, or well, no, rather homology. I've taken homology. Of X is more, the X is like the space of all pairs of polynomials. So that's more twiddle, but tensored with homology of P1, this is what a column of the spectral sequence is going to look like. And the reason this guy appears is that this is like a symmetric product of suspension of n, right? So taking suspension shifts the degree and gives you exterior powers of the homology of P1, because the homology of P1 is only supported in even degrees. And in turn, what you end up is that this spectral sequence converges to the cohomology of U, which is the honest-to-God morphisms or holomorphic maps from P1 to P1, the pairs of polynomials having no common zeros. And this spectral sequence has non-zero terms only in the first three columns, because the homology of P1 is just a two-dimensional vector space. It doesn't have much space to go beyond that. And all you have is a spectral sequence with a couple of columns. The differentials are naturally given by like alternating sums of chain maps. And the result is as something as simple as, so unlike in Siegel's case where you get stable homology, you get the full cohomology here. So I initially made the computation cohomologically. I will just write it down. But with ring structure, it is simply QT modulo T squared, where T has cohomological degree 2. I am computing it rationally because mainly what I care about is rational or QL coefficients, because that's the only thing sort of arithmetic side cares about. But nevertheless, yeah. So this is a demo computation. And this method works for like you can have the target space to be pretty much whatever else you can think of. The spectral sequence, a spectral sequence like this can be still formed because this part is part of the theorem. Okay, I'll stop now and let people ask questions because I have introduced way too many symbols near the end, right? Just in stating the theorem and giving a demo computation. So I'll stop here. Okay, I'll stop here and let you ask questions. Thank you.
All right, let's thank Oishee for an interesting talk. Any questions from the audience?
I'm not sure.
I have one. So, yeah, so can you go back to the two questions you have?
The two?
I think yeah, there were like two questions. So the second question is when y is like a stack, not like varieties or, yeah, that one. Is there like is there like a number theoretic reason why you care about that particular y?
Very much so. Yeah, there are the moduli space of genus one surface with a marked point is actually so I should write this down. Moduli space M11 bar is actually isomorphic to this weighted projective space P46, where like T0 is 4, T2 is T0 is 4, T0 is 4, T1 is 6, and like N is just 1 here, and this gives you what is called the count of stable elliptic fibrations over a curve, and this sort of this general theorem works to give you the exact number of stable elliptic fibrations over a finite field, which is a result in with my June Park and Johannes. So it has number theory.
Cool. Any other questions? Another thing on my mind. So you said like the theorem you stated is a special case. So how, like, I guess how much more can you make it? Like, how much more general can you make it?
Right. Great question. One simple way one can generalize this thing is that instead of having a graded monoid, you can have a partial monoid of the form like sim M1 disjoint union sim M2, something like that. And in fact, that is precisely the case that comes into play, like being a module over a graded partial monoid is what comes into play if you want to have estimates about something like a toric variety. I mean, not all toric varieties, but there is something called a complete simplicial toric variety, which is defined by simply its combinatorics. It's defined by having what is called a certain number of rays and simplices and so on. And in that case, one can have a complete computation of the cohomology, not just the stable part, but you can sort of generalize it to partial monoids. The other bigger generalization is that, as you can see, these things are mostly motivated by algebra, geometric, and number theoretic questions, in a sense. And one of the goal is to do right by the geometric situation, in particular Hodge theoretic situation. So the other generalization is that the whole game can be played not just in terms of having a module over a monoid in the category of topological spaces or schemes, but more generally, things like schemes over a space S. So like M is a space over S, like M to S is a map. X is a module over sim M, but in the slice category of spaces over S, and in that case, there is still a derived tensor product giving you the intercomposables, but this looks slightly different, and so does the Sheehy version of that. But that's the maximum generalization that I wouldn't say that's the maximum generalization one can do, but at least that covers whatever purposes we want.
Okay, sweet. Please.
I have a question.
Yes, please.
Does your new spectral sequence allow you to do something for in regards to the battery of Manin conjecture?
Yes. So this spectral sequence, it verifies the geometric Banerjee type conjectures for all complete simplicial toric varieties and weighted projective stacks by so the spectral sequence. So the version, so it confirms that, so what geometric Madam's conjecture would say is that you have Q to the, like over finite fields of Q, you have Q to the dimension of the space as the leading term in the point count. And the geometric Madam's conjecture can be verified for the case when Y is, I have personally worked out the case of Y being complete simplicial toric varieties and like weighted projective stacks with some other people. But I could say exactly what cases this works out. So complete projective toric variety, weighted projective stacks, and it should work out. So spectral sequence also applies to confirm geometric Madin for like flag varieties. But what it does not do is spectral sequence is not enough to compute or to confirm geometric Banerjee conjecture for low degree hypersurfaces, Fano hypersurfaces, or hypersurfaces which are Fano. So to answer your question, not all Fano varieties is confirmed by the spectral sequence. Absolutely not, because it involves knowing the cohomology of those particular varieties and the mapping spaces. And but the spectral sequence works for like certain blow-ups of projective spaces that these toric varieties circumscribe. Like
so it covers Del Piazza surfaces, for example.
It covers those del tensor. I haven't worked it out. It's not written anywhere, but it covers those del tensor. It should cover those del tensor surfaces which has a universal tensor. Yes.
I see. Cool.
Yeah, having the universal tensor situation sort of lets you to like, one can construct the spectral sequence, but one has to sort of bound the unstable part of the cohomology to be able to say about point counts, right? So having the universal tensor lets you bound the unbounded, unstable part of the cohomology in a way. I'm also aware of some people working on like blowing up projective planes over any number of points. So like, in turn, they would give rise to like things outside of deltas as well in particular. But the catch is that they have a homological stability result, but they are unable to bound the unstable homology. And in turn, Manin's conjecture cannot be confirmed there.
I see. Nice. Thank you. Very good. Yeah.
Awesome. All right. So let's thank Oishee again.
Thank you, Oishee.
Let me stop the recording. Boom.